huge aircraft carrying lots of people, long distances, have massive engines.
But it's no good having a really powerful engine if it weighs a ton. Aircraft engines are all about power to weight ratio. They have to be powerful, but also light enough to fly.
How did airliner engines evolve from small car-like motors into massive monsters like this? This is one of the very first airliners. It's a 1920s Ford trimotor. But even with 3 engines, this plane still needs a runway 2,500 feet long. And that's the thing about aircraft engines, they've got to get off the ground.
Powered flight just couldn't happen until this came along, the petrol engine. Before this was invented at the end of the 19th century, the only engines available were steam engines, powerful but just too heavy.
Petrol engines like this have a great power-to-weight ratio because their fuel comes ready to use, unlike steam engines that have to carry around a huge great boiler and water reservoir to create it. In a petrol engine, a mixture of fuel and air is sucked in through the carburetor into the cylinder. It's compressed by the piston and then ignited by an electric spark plug here, and the resulting explosion forces the piston down, which ultimately rotates this crankshaft at the bottom. Stick a propeller on the end of it and you've got yourself an aircraft engine. So in 1903 it was a petrol engine that enabled the Wright brothers to get the world's first powered plane into the air. They'd worked out that they needed an engine that produced 10 horsepower yet weighed no more than 200 pounds. Unfortunately, on the market at the time, there were no engines that met these exacting demands. So, what did they do? They built their own. The first petrol aircraft engine was born. They went for 4 cylinders in a line, the power being transmitted to the propeller by a chain. They kept it cool by running water around it from a radiator. It was an engine that for the first time in history was powerful enough and light enough to lift itself and a single human being into the air. But it couldn't carry any passengers. For that, you needed an engine with an even better power-to-weight ratio. This engine had a brilliant power-to-weight ratio. It's a rotary engine invented by Australian Lawrence Hargrave. And just 10 years after the Wright brothers, they were powering the fastest fighters of World War I. Rotaries work on an utterly mad principle. You'll notice that the cylinders are rotating with the propeller. The propeller is actually bolted to the cylinders, and the only bit of the engine that's actually bolted to the aircraft is the crankshaft. If you were selling this aircraft, you wouldn't put down under the photograph, easy starter. It weighed 290 pounds. That's 50% more than Wright's first aero engine, but rated at 160 horsepower, it was 13 times more powerful. And by arranging the cylinders in a circle like this, they were all exposed to a steady stream of cold air coming in from the front, so no need for a heavy water cooling system, improving the power-to-weight ratio even more. Unfortunately, with these crazy engines, you could only build them so big. Any bigger, and the gyroscopic forces created by all that spinning mass would literally rip the engine off the front of the plane. So they were great for small fighters, but just not big enough to lift a payload of passengers, as demanded by the new craze for air travel that sprang up after the war. But a sanitized version of the mad rotary would form the main engine of big airliners for the next 40 years. The radial engine. Radial engines were perfected by Frederick Brent Rentschler, who set up his company, Pratt & Whitney, to build them. They had one major difference from their rotary engine cousins.
On the rotary engine, you've got your propeller on the front, and the whole lot would move round with the propeller, like so. But with a radial engine, a standard radial engine, the propeller will be stuck on the end there, and this bit wouldn't move. I used to think I was good at impersonating aircraft engines, but pretty crap against the real thing.
Like the rotary engine, the radial was air-cooled, keeping it light. But because it didn't spin, it could be built much bigger. So it was radial engines that powered the pioneers of air travel like this 1920s airliner, the Ford Trimotor.
There's 3 of them on this aircraft, 1 up front and 1 on either wing. Magnificent.
Each engine weighs 650 pounds, about 3.5 times more than the Wright brothers' first engine, but producing nearly 35 times as much power. At last, here was an engine type whose power-to-weight ratio was good enough to get a plane into the air and carry lots of passengers too.
In the early days, it was expensive. In 1926, if you flew from London to Cape Town, it would cost you £130. That's £10,000 in today's money. And you went via France, Italy, Greece, Egypt, Sudan, Kenya, Tanzania, and Rhodesia. And you'd sit in one of these seats. Take a look at these. Absolutely magnificent. A quality item. With actually a little bit of recline as well. About 2 centimetres. And of course, the noise levels on board a plane like this are pretty intense, but then who needs in-flight entertainment when you've got the music of the Pratt & Whitney Wasps? Not me, that's for sure. Tea or coffee, sir?
It was still a mad plane though. The one we flew in generated an ever-growing pile of nuts and bolts that built up in the aisle. Ladies and gentlemen, you'll find a life jacket under every seat, and a set of spanners. But the biggest and most luxurious of all the airliners to be powered by the radial engine were the mighty flying boats, carrying up to 50 people.
You could have anything you wanted. There were bars, dining rooms, sleeping quarters, smoking decks. Some even had grand pianos. Cheers. Shocks away, Ginger.
At the time, the flying boats were the biggest planes ever built. And they were powered by the biggest engines. These are radial engines, but not as we know them from the Ford Trimotor. This is a Pratt & Whitney Twin Wasp engine, one of the most efficient and reliable engines of the 1930s. The Twin Wasps had 14 cylinders, as opposed to the 9 found on the standard Wasps that powered the Ford Trimotor. But really cleverly, the 14 cylinders were arranged in 2 banks of 7, with 1 row of 7 directly behind the other. So, although the engine was bigger and much more powerful, the front of the engine was more or less the same diameter and didn't create any more wind resistance. Each of these engines weighed 1,500 pounds, twice that of the Ford Trimotor's Wasps. But these generated 3 times more power, 1,200 horsepower.
It's all very well having the most powerful engines, but you've got to translate that power into usable propulsion.
And the key to that is the design of the propeller. In World War I, propellers were like this, solid. But on the 1930s flying boats, they were like this, the variable pitch propeller, which means that the propeller blade changes automatically its angle of attack, or pitch, depending on the speed of the engine. With these so-called hydromatic propellers, the 1930s flying boats had a range of 3,000 miles and could get you from San Francisco to China in 6 days.
So, why were they flying boats and not land planes? Well, mainly because the planes were so big, there weren't enough long runways on land for them to operate on. Landing on the water, the runways could be as long as you liked.
But with World War II just around the corner, the flying boats' days were numbered. Airliners and aero engines would soon change beyond all recognition. Why? Because of this. Frank Whittle had invented the jet engine. The invention of the jet engine would change air travel forever. Airliners were about to get much bigger and much faster.
This is a jet engine. It's a jet engine you can hold in your hand, but it is nevertheless a jet engine. So, how does the jet engine work? Well, inside this casing, you've got one of these, which is a shaft with a turbine on the back and a compressor on the front. Now, once this is set in motion, the compressor sucks in air through the front of the engine. That air is then squashed and compressed as it moves further and further into the engine. When it gets to the combustion chamber in the middle of the engine, fuel is added to this air, and the whole lot is ignited by a giant spark plug. The resulting explosion forces gases out of the back of the engine at great speed. Then the whole lot goes that way. Now, the amazingly clever thing about the jet engine is that it's self-perpetuating. As the gases are forced out the back at high speed, they drive the turbine, which drives the compressor on the front of the engine, which is sucking in the air in the first place. Suck, squeeze, bang, blow. Brilliant.
But a jet engine is just a fancy tin can until it's running.
Move that to allow you to actually start the engine.
I'm moving that throttle forward in traditional manner. And there we are. I can hear a distant spin, and there comes the jet in. There it is. We're going up and up and up, and yes, we're getting to 120,000 RPM. And the exhaust gas velocity is 600 miles an hour.
That's why it's so loud. The air blasting out the back literally tears the still air around it. And it's the ripping air that's making the deafening noise.
But it's not as loud as the real thing.
This is a Gloucester Meteor, the world's first operational jet fighter. It went into service in 1944, powered by one of the very first jet engines.
It was invented as far back as 1929 by Frank Whittle, a flight lieutenant and test pilot in the RAF, but the concept was so revolutionary, the Air Ministry didn't want to know.
Jet engines were so different to the old piston engines, it was like comparing apples and pears.
It was only when the jets were put in flying test beds like this Gloucester Meteor that jet engines and piston engines could really be compared. And they found that it wasn't like comparing apples and pears, more like comparing apples and very large melons.
Jets work more like a rocket engine. An internal explosion drives gases out the back and propels it forwards. Because of that, they're not measured in horsepower like the piston engine, but in the same way as rockets, in pounds of thrust.
The new jets were light, simple, and although they'd need a lot of development, they had the potential to go fast, very fast. Partly because they didn't have propellers.
With a propeller, it's very hard to go much over 400 miles an hour. Faster than that, and the propeller stops working properly. It just can't grip the fast-moving air around it. In 1945, a Gloucester Meteor was clocked at 606 miles an hour. That's 150 miles an hour faster than a propeller aircraft had ever been.
So, we've heard the miniature jet engine, pretty loud, very loud in fact. I wonder what the real thing's like. Sticky starter motor. We've all had that before. Go on, my son.
but classy. Classy, with presence. Not only were the new jet engines faster than the old piston engines with a superb power-to-weight ratio, they also operated much better at altitude. The thinner air gave a less bumpy ride, and with less air to power through, less fuel was needed, which brought costs right down. This made jet engines perfect for airliners and would condemn the old piston engines to graveyards like this old hangar we found in Florida.
And where do you start in this room? It's just absolutely unbelievable. Yeah, my Riley 1.5 needs a new engine. What should we have?
Some of the greatest engines ever made are kept in here.
The Pratt & Whitney R2800 would have found that in DC-6 and many other aircrafts from the end of the war through the 50s and onwards. Further on here we've got the Bristol Centaurus engine, a great engine, powering some of the most powerful fighters of the Second World War, the Sea Fury, among others. Perhaps the greatest motor of all, if we're talking as we are about massive engines, is the largest piston engine for an aircraft ever made, and it's the Pratt & Whitney R4360. This lump powering some of the most massive, the ultimate piston-engined aircrafts.
Like the final version of the Lockheed Constellation. But the Constellation could only do 320 miles an hour. New jet airliners, like the de Havilland Comet, could do 520. The jet age had truly arrived. The all-powerful jet engine let airliners attain the vast size of the jumbo jet, and the engine's cheap kerosene fuel kept costs down. Jets opened air travel up to the masses. Rolls-Royce are one of the key jet engine manufacturers, and this is the most powerful airliner engine Rolls-Royce produced today. The mighty Trent 800, designed to power the new generation of transatlantic twin-engined airliners like the Boeing 777, capable of carrying over 350 passengers. These so-called super twins are only slightly smaller than jumbos, but only have 2 jet engines as opposed to the jumbo's 4. So, the 2 engines have to be absolutely massive. And as you can see, this engine is absolutely massive. This engine generates a phenomenal 100,000 pounds of thrust. That's nearly 50 times that of the Meteor. Part of the reason this engine is so much more powerful is because it's got this socking great fan on the front. Now, this socking great fan not only drives air into the jet compressor here, but it also drives most of the air down the side of the engine, acting in effect like a propeller. The fan lets the engine suck in more air than there is in a squash court every second. And as well as providing more power, it's also quieter than a traditional jet. Nearly every jet airliner flying today is powered by massive engines like this. So how do you build something like that? The answer isn't necessarily quite what you'd expect. This is the Rolls-Royce jet engine production line. Here, all manner of jet engines are produced, including the mighty Trent 800. But look, it's not a robotic production line like you'd find in the average car plant. Each engine is hand-built from the bottom up by a team of 5 men. Gradually the engine is built up in sections vertically, a bit like a giant wedding cake really. This is the squeeze, bang, blow part of the engine core. Compressors down here, fuel pipes, combustion chamber in there, and turbines at the top. Now, above everything else in this assembly shop, this Trent 500 core carousel says to me Rolls-Royce quality and organisation. Nowhere is there to be seen an ancient St. Bruno tobacco tin full of crap. Before one of these engines can be installed on an aircraft to power us all the way down to Majorca and beyond, it has to be tested. And that's where I'm going to now. outside to one of the test buildings. Drive on, sir. We'd get there a lot faster if that Trent 500 was running at full whack. There, above me, suspended from a massive crane, is a massive Rolls-Royce Trent 800 engine about to be tested. I truly feel that I am in a cathedral to power. Under test, this engine is operated way beyond the level that would be required in everyday service. It's basically taken on lots of little flights, takeoff, cruising and landing. But at 100,000 pounds of thrust, you've got to ask yourself the questions, how strong does that crane have to be and how much noise does this engine make? The answer is a lot, but in the control room just about 10 feet away you can't hear a single thing thanks to the soundproofing qualities of these giant double doors. Double glazing, sir? PVC or wood? Or concrete and steel composite? Certainly keeps the burglars out. So here I am in the control room. There on the screen is the engine we're testing. In reality, that engine is round about 20 feet away on the other side of those double doors. And here I am at the controls. And of course, to control the engine, we have a throttle lever just like the one you'd find on a real aircraft. So let's rock. Gently does it. Let's not overload it too quickly. Bit by bit, increase the power. Right the way up to full power. There we are. 100,000 pounds of thrust. Airliners have transformed the way we travel, making all parts of the world accessible to the masses. It's incredible to think that at any given moment there are over 500,000 people travelling on jumbo jets alone. Good morning, ladies and gentlemen. This is your captain speaking, welcoming you aboard this flight to Munich today. And take off. Full power.